Okay. Let's move on to a homework question. I bring this up because it requires you to use something that I spent very little time. I basically had on, pointed to it, and moved on to my lecture on, what did I lecture last Friday? No, I lectured on Wednesday. So on Wednesday. So this question here, and some of you were working with our tutor Jordan, and he was working on this, and he was not doing it correctly because he forgot that the equation that we first saw is only correct if temperature is constant. Now, those of you in calculus actually don't have the problem I'm looking at. You have another version of it. But if you used calculus, the correct equation is ds is equal to dq over t. And then you have to integrate. Well, I don't expect people who aren't in the calculus class to do the calculus. You're welcome. So here's the slide that I had in the last lecture. And we have the solution if it's isothermal. That's the one everybody understands. We have the solution if it is a solid or liquid that's heating or cooling. That is where heat is equal to mc delta T. And then we have one for gases that are undergoing an isochoric or an isobaric process. And so for this problem, which case do you have? Is it constant temperature? Is it a solid or fluid that's heating or cooling? Or is it a gas undergoing an isochoric or isobaric? You're mixing water with water. Heat flows out of the hot water into the cold water. Which of our situations is that? Going back to our situations, is it, okay, I have two of them in red boxes. Let me change color. One in a green box. Here, I'll change that one to a black box. Which box is it if we have a liquid that has its temperature changing because it's being heated? What color? The red one. So that's the equation that you should be using to find the change in entropy. Now, in this problem, you have, I think everybody has the same mass, which makes life easy. Because if you have the same mass of the same material, where's the end temperature going to be? Halfway in between. So you can find the temperature real quick. It's going to be halfway in between. Of course, you could have used, MC, mass 1 times C of water times temperature final minus temperature 1 initial plus mass 2 C of water times temperature final minus temperature 2 initial, and you would have found it really quickly. But you can find the final temperature really easy. It's halfway in between. And then you have to have the mass of the water, the specific heat of the water, and you use that to find the change in entropy for the water that cools, find the change in entropy for the water that heats. The sum of those two is the total change in entropy. And if this is a naturally occurring process, what can you tell me about the answer before you start? There's one thing you can tell me. It's got to have the entropy goes up. The final answer has to be a positive. So you're going to have one is positive, one is negative, but the positive has to be the bigger. Now, some people might say, is there another way? There is another way that's approximate that actually turns out to give us very close to the right answer, although sometimes it's very grossly wrong. And that is to say, well, since it wasn't constant temperature, how about if I just use the average temperature? If you had done it using the average temperature for the cooling portion and the average temperature for the heating portion, you would have been within the margin of error that's accepted with expert TA. But it's actually more work to do it that way as well. So I just want to go over this to make sure people understand these equations here for change in entropy. Because it is a heating or cooling of a solid or liquid, we have to use that equation to calculate those entropy changes. Now, on with the show. You got your clickers ready? Because I have one repeat slide and then a clicker question. The one repeat slide is the slide that shows a simple harmonic oscillator. That is, it shows something like this that we go boing and it vibrates back and forth. Now, this is a damped oscillator because it doesn't keep going forever. It stops quickly. A tuning fork is doing the same thing. Which reminds me, somebody in biology borrowed my tuning forks and never brought them back. I need to go hunt them down before lab on Tuesday. So, to have simple harmonic oscillation, remember, simple harmonic is the special kind of oscillation that gives you a sinusoidal motion. What does sinusoidal motion mean? It means you have this nice looking pattern if you look at the displacement. So this axis is displacement. And this axis is time. And we have to define what displacement is. It's a new word. Displacement, okay, you probably have in your brain a reasonable facsimile of the definition of displacement. Displacement is the motion away from the equilibrium position. So in this situation, I have a vibrator, something like this, that has its equilibrium position is horizontal. So if I push it down, I displace it about a centimeter down. So my displacement is a centimeter down. I let go and it vibrates up and down. The distance it is from the equilibrium position is the displacement. And it can be positive or negative if it was up or down. So the displacement is going like this, and it's described by an equation that says x is equal to a sine of omega t. A is the amplitude. Amplitude is the maximum displacement. So the amplitude is the maximum it was displaced. And notice that that's symmetric. The sine function goes between -1 and +1. So when you have a simple harmonic oscillator, its displacement goes between the plus amplitude and the minus amplitude. So in this picture, where is the amplitude going to be found? Okay, the peak. So here's a peak. Down to where? Not to the trough. The peak to, somebody said, the average, the equilibrium position. So the peak to peak, what Ashley said, is 2 times the amplitude. Sometimes we measure peak to peak, so it's important to have these things in your head. So we usually do something like this. There's my amplitude, and there's minus my amplitude. Omega, we've seen the symbol omega before. What did we call omega last time we saw it? The angular velocity. Well, now we're going to give it a different name, but it's the same stinking thing. It's now called the angular frequency. That angular frequency tells me that it has units of angle per time. So the units for omega angle over time. What's the natural unit of angle? Radian. Technically, a radian is no units at all because angle has no units. So radians per second are the units for omega. Now we have another symbol that we use quite a bit. Frequency. F is just the regular frequency. Its units are cycles per time. Well, one's angle per time, one's cycles per time. We have a simple relationship. One cycle has how many radians in it? 2 pi. And so I can relate this angular frequency to the regular frequency. The angular frequency is equal to 2 pi radians per cycle multiplied by the frequency. If you see Hz, that stands for hertz. And hertz is defined as inverse seconds. 1 cycle per second is what hertz means. So frequency in hertz, cycles per second. Angular frequency in radians per second, which is just 2 pi times the frequency. Some other things to see on this picture. I have time on the horizontal axis. A very important time is the time for something to repeat. We call the time to repeat the period. Now I can measure the period from any point to when it's exactly reproduced. So let's say I start right here. I start when my displacement is 0 and it's going to positive displacement. If I want to find where it repeats, I'm going to go to where the displacement has what value? 0 again, because I need to have it repeating, but also it needs to be going the right direction. It starts going from 0 to positive, so I need to have it going 0 to positive for it to be repeating. So I don't just go from 0 to 0, I go from 0 to the next place is 0 to positive, and that's the period. So the time from here to here is the period. And the symbol for period is a capital T. So from this graph, I can read the period and I can read the amplitude. Going back to the slide, all that I intended on the slide was to remind you the condition necessary for this sinusoidal motion is that the net force in the object is minus a constant multiplied by the displacement from the equilibrium position. So K is the constant, delta X is the displacement from equilibrium position. The minus, very important, means that it's a restoring force. It's a force that's going to try to bring my oscillator back to its equilibrium position. So it's a stable equilibrium. Everybody understand what's on the slide? Okay, let's do our clicker question then. What 2 conditions, obviously you're going to answer 2 answers and hit enter, are necessary for the net force on a simple harmonic oscillator? The shuffle forward. Okay, I still don't have Ashley, Corso, Rebecca, Eric, James, Amanda, Augusta, Edward. Some of those have come in. Okay, still missing Augusta and Edward. And James is still, there you go. Do you have Augusta? Okay. And, okay, we're all in. So we have quite a spread. 6, 12, 5, 5, 0, 7, 11. So turn to your neighbors and see if you can come to some more concrete, clear answers. 2 of them are correct. You know, there's about a 1 in 2 billion chance this is going to work. I like my odds. No, it's not Microsoft. It's Turing Technology. So let's see if more than one. No, only one person gets the answer. And that person only answered one answer. Well, you knew there were 2 answers. I told you the 2. So let's go to Corso for some clarification.
What?
Name one of the 2 correct answers in your opinion and your reasoning.
Number 11.
You mean G?
G.
Why?
I think that's what we discussed.
Because that's what we discussed.
Sure.
Okay. I will expand on that after Ashley gives us what she thinks is the other correct one.
Well, after talking to my neighbors, I think it's B. The net force must be proportional to this displacement because it matches with
Because it matches with
the equations.
the equation. That's a good answer. This is the equation. We have a minus sign, so that means the force has to be in the opposite direction of the displacement so that it restores it to equilibrium. And the other answer is what Ashley said. It matches the equation because that is not squared. That is not 1 over. If we look here, net force must be constant. Well, that would be force net equals constant. There'd be no x there. Net force must be linearly proportional. That's a linear proportionality. Proportional displacement squared, no square there. Inversely proportional, that would mean it'd be 1 over delta x. It's not. 1 over delta x squared, everybody agreed it wasn't 1 over delta x squared. Good. Net force must be in the same direction. Well, that minus sign means it's opposite direction. So the 2 correct answers were B and G. Okay, those are important, right? To understand what causes simple harmonic motion. Now, the energy in a simple harmonic oscillator. We learned about energy, kinetic energy, energy in motion, potential energy, energy because of configuration or position. In a simple harmonic oscillator, you have both kinds of energy. So take, for instance, a spring. I use a spring because what's the equation for force that is produced by a spring? Kx. So if I put a mass on here, it's going to put a downward force due to gravity, and the spring is going to stretch a distance that depends on what that is. And now the spring is stretched. It has energy stored, potential energy. And so this graph is showing for the non-calculus people how calculus people determine how much energy is stored in that spring. They take the integral, adding up, the force times distance for every little piece that it's stretched. You put it all together, and you have the area under this line is equal to the work that was done to stretch that spring. And since change in potential energy is equal to work, that means the potential energy is equal to the area under that triangle. Well, for a triangle, the area is 1/2 base times height. The base is x, how much it's stretched. The height is kx. So 1/2 x times kx gives us 1/2 kx squared. So the work done to stretch the spring is 1/2 kx squared. And thus the potential energy for a spring is 1/2 kx squared. That's how much energy is stored in the spring, the amount of work that was done on it to stretch it. So if I take this and I pull it down, there's a restoring force. That means there's a force that's going to pull it back up towards equilibrium position. When I let go, what's going to happen? It goes up and it'll oscillate back and forth. Now I have a simple harmonic oscillator. And you see it keeps going. There's a little damping. Damping is energy removal. Air is going to damp it a little. Also, the spring is not perfect. It's also going to damp it a little. So eventually it'll stop. But it's undergoing simple harmonic oscillation. If I make a graph of its position, its displacement about equilibrium as a function of time, we'll just see this nice sinusoidal pattern. Energy is now being transformed between spring potential energy and gravitational potential energy and kinetic energy. So I'm having energy going back and forth. So the total energy of the oscillator is staying roughly constant. It's slowly decreasing because of damping. But the total energy is staying pretty constant, but shifting back and forth between potential and kinetic. A car should not drive like this. If you have bad shock absorbers, a shock absorber is something that damps the oscillation. It takes away energy from the oscillation. So on your cars, anybody know how to check to see if your shock absorbers are bad or not? Okay? You go and you push down on the fender. If your shock absorbers are bad, what happens? It keeps bouncing. What I was taught is if it comes up more than 3 times, your shock absorbers need to be changed. Because the shock absorbers are supposed to take away the energy. Well, why is it bouncing to begin with? Not curse the road. The car was just sitting here, and I came and I pushed down on the fender. We have springs in there because when you're driving on the road may not be perfectly smooth. Here in Lincoln, especially come wintertime when we have freeze-thaw cycles, we develop big canyons in the road, right? You'll have a hole that's bigger than your tire and that's a foot deep. Well, you want to try to minimize the effects of that on your ride. You want it to be comfortable. So they have springs attached to the tires. And so when you hit one of those, boing, it goes down, gets the other side, boing, it comes up, and the spring is allowing the car to not fall as much as the tire did. But of course, the result is the car is going to start bouncing because you got a spring in there. You have a simple harmonic oscillator. And so it has the shock absorber to damp it out, to take the energy out, so you don't just keep going like this down the road after you hit a pothole. So it's a very practical system. This here is also a damper. It's something to take away the energy from the door as it's closing so that the door doesn't just slam shut. There is a spring to pull it closed. If there wasn't a stopper, the door would go back and forth, back and forth. Put a damper in there so that it doesn't do much. That's what we call an overdamped system. Actually, it's pretty close to critical damping. This is definitely underdamped because it's still oscillating. I've already talked about this. We talked about the period. I did not talk about the connection between period and frequency. Frequency, how many cycles per second? Period, how much time per cycle? Well, if you put that in your head, time per cycle is period, cycle per time is frequency. So they're just inverses of each other. So the frequency is defined as 1 divided by the period. So if you know frequency, you obviously know period. If you know period, you obviously know frequency. And we've already talked about the relationship between the angular frequency and the regular frequency. Given the definition for period, you can also then have between angular frequency and period. Second, simple clicker question. What are the units of angular frequency? This one has only one answer. Oh, no, it doesn't have only one answer. It has multiple answers. I'm sure you guys don't keep count, so you don't know who this last person is, but this is the only person who has not been called on twice. Nice.
B and C.
Well, wait till everyone answers. Okay, Arlene. Okay. So we had 0, 17, 11, 15, 0. And nice, what did you say? Not that she's hedging her bets or anything. But she said, if any of you said it, I'm with you. Now, it is not B, C, and D. It is not B, C. It's just D because that's the only one with.
You say there are multiple answers. You can't.
Yeah, it's accepting multiple answers because if you forget that it's angular, then you could have answered B or C. And so I had to. This is for a learning experience. It's not for a testing experience. It's, you know. And so the correct answer there was rads per second because it's angle per time. What are the other two? These are exactly equivalent because a hertz means 1 over second, and that's just regular frequency. Okay, let's go past there and past, well, no, let's not go past here. If you have a simple harmonic oscillator, I said that by definition of a simple harmonic oscillator, you have to have the net force is minus kx. That's the definition necessary for a simple harmonic oscillator. That means your acceleration, right? If you take this equation, divide everything by m, your acceleration has to be minus k over m times your displacement. Now comes the kind of tricky part. For simple harmonic oscillators, your position is defined as a sinusoidal function. Your displacement is amplitude times sine of omega t. If you take a sinusoidal graph, whoa, it was growing. That was inappropriate. So I have displacement versus time. And now I'm going to say, what's the speed if I have a displacement versus time graph? How do you find the speed on a displacement versus time? This goes back to the first lab. Or second lab, I thought it was first.
The slope.
The slope. So the speed is going to be the slope. Where is the slope the steepest? Where? When it crosses the axis. So here, 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 those are the steepest slopes. The first one is positive, so my speed is going to be a maximum here and a minimum here, a maximum again here. What about where's the speed 0? Where's the slope 0? The trough and peak. So it's going to be 0. And now I just have to connect the lines in a nice smooth sinusoidal graph. And so that's what the speed looks like. It looks just like the displacement, but it's shifted. And of course, the amplitude can be different because the speed, of course, is going to be different. Now, if we have calculus, we have the speed is equal to the slope is equal to the derivative of the displacement. And we get the equation that says the speed as a function of time is equal to omega times the amplitude times cosine of omega t. Now we could go through the same process. How do we find the acceleration from a graph of speed versus time? It's the slope again. Or with calculus, it's the derivative. So acceleration is equal to the slope slash or derivative of speed. So doing the same process, we find the acceleration as a function of time is equal to minus omega squared a sine of omega t. But then you look at that and your busy little brain says a sine of omega t, that's what x is equal to. And so we have the acceleration is equal to minus omega squared x. That's just a result of it being a sinusoidally varying function. And so let's combine this acceleration is minus omega squared x with acceleration is minus k over mx. And that tells us that omega squared must equal k over m. So omega must be the square root of k over m. So if I take this right here, it's a spring. I can calculate the spring constant by stretching the spring, measuring how much force I put on it, how much it stretched. I can find the spring constant, measure the mass that I have on it, and I find the angular frequency. What's going to happen to this angular frequency if I put more mass on there? If mass gets bigger, what happens to omega? It's in the denominator, so it's going to get smaller. So we can test that. We can take this, and somebody want to get out their smartphone, because I know none of you have it out right now, and go to your timer, and we'll time the period by measuring the time for 10 cycles and dividing by 10. So it looks like Corso, you can do this for us?
Yes.
Okay, so I'll tell you when to start and stop. Start. Stop. Okay, so what was the time for 10 cycles there?
7.75.
So we had mass equals 100 grams, and the period is equal to 7.75 seconds divided by 10 because we did 10 cycles. Now I'm going to go from 100 to 200. doubling the mass. What do you predict is going to happen? What's going to happen to the period when I do this one? It's going to be what? Okay, period's going to increase, Alex says. Right? We always want to have an idea what we think should happen by theory. So you ready, Corso? Okay, so again, I'll tell you when to start. Start. Stop.
10, 20, 22.
Okay, now that went up, but it didn't double. Why didn't it double? Why did the period not double when I doubled the mass? Because what? It's not a linear relationship. It's a square root relationship. So it should be proportional to square root of 2. What is, well, 10.22 divided by 7.75. What is that number? If we square that, in theory, we would get 2. In fact, it's going to be a little bit below. Because, well, we didn't take everything into account. But we can see that the angular frequency varied with mass. The period should be equal to 2 pi over omega. Yeah. And so the period went up as omega changed because of the mass. A simple pendulum. The last thing for today is simple pendulum. This here is a simple harmonic oscillator. We can see the relationship between the position, the acceleration. Notice I didn't spend time on this. The maximum speed is this. So V max is equal to omega times amplitude. Maximum displacement is obviously amplitude. And acceleration max is equal to omega squared times amplitude. We have simple relationships between omega and the amplitude and those variables. Shift to a pendulum. So here's a pendulum. I have a string of some length L. Hanging from it, I have a bob, a stopper. And I can pull this out here. Gravity, what direction is the force of gravity on this bob? Straight down. There's also another force due to tension that's up this way. It's going to accelerate in what direction? The only direction it can move. So I let go, and it swings back and forth. Now the question to ask is this a simple harmonic oscillator? If I look at the pendulum, we see that if I break my force of gravity into components, I have one component that goes like that, that's exactly opposite of the tension. And in that direction, if I call that my y direction, the sum of the forces in that direction has to be 0 because it's not going to accelerate in that direction if the string isn't stretching. The other component is going to be mg sine theta. And so if I look at this as, is it a simple harmonic oscillator? The net force on that bob is mg sine theta minus for the direction. And so I have minus mg sine theta. What is my displacement? Well, I would generally consider my displacement x, the distance along the arc length. And for a circle, the arc length, there it says s, so I'll use s. S is equal to theta times the radius, which in this case is L. So I can rewrite this as force net equals minus mg sine of S over L. And now you tell me, is that a linear function? We had two things. It had to be restoring. Is it restoring? Yes, it has the minus sign. Is it linear? Sine is not a linear function. And so we say fail, ultimate failure. But not so fast. For small angles. So this is only for small angles. Sine of S over L is equal to S over L minus S over L cubed over 3 plus blah, blah, blah. Well, if S over L is small, like 0.01, and then I take the cube of that, that's 10 to the minus 6, it's negligible compared to S over L. So for small angles, this stuff out here is approximately 0. And for small angles, sine of S over L is just S over L. So for small angles, this becomes force net is equal to minus mg S over L. And now we can identify, aha, mg over L is my K. And so if mg over L is my K, then my omega, it turns out the mass cancels. It doesn't matter what the mass is of the pendulum. My omega is just square root of G over L. Okay, we're out of time. So you'll have homework problems that deal with simple harmonic oscillators, either a pendulum, remember the pendulum, it has to be a small angle for it to be correct, or a mass on a spring.